Okay, there you go. Electrical systems in buildings. Well, I have taken that picture from uh, here. We have the PV array, and well, this is an electrical system as well, and this affects the design. Okay, so little by little, architects we have to find ways to integrate renewable energies on our buildings. So this is a challenge. Nobody has done it before. There are examples, but we don't have a recipe. We can't say, oh, you have to do this. With drainage or mechanical systems, we have recipes or we have tables. Okay, if you connect two 1 inch pipe, the result has to be 1/4. Okay, so those are recipes, and if you do this, because we have experience doing this, it will work. But when it comes to integrating renewable energies in our buildings, we don't have experience. So we are pioneers. So we are doing something that people had not before, had not done it before. And yeah, and it's always, we need to find ways to do that. How long will it take to find a recipe or something that we can replicate or reproduce in other buildings? I don't know, decades probably. So maybe in 10, 20, 30 years, designing buildings, integrating renewable energies will be like, okay, what do I have to do? You have to do this. Okay, so I place 100 panels, and I need this wire, and I need this here, and the orientation. But nowadays, we have to deal with it because we have this goal of zero energy buildings in 2050, in 30 years, and we don't know how to do it. Well, we know how to do it, but we have the challenge to produce good architecture. So from the engineering point of view or the calculations point of view, designing zero energy building, it's easy. But now we have to design good architecture that is a zero energy building as well. And this is not as easy as it seems. Anyway, this is an electrical system, and the PV array has to be connected to the electrical system, our building electrical system. Mm, and also this PV technology has been here for 50 years. Integration is not solved yet. It's solved from the electrical point of view, but not from the architectural point of view. Anyway, let's start looking at global perspective. Okay, so we are looking at the world. This is the world. And what is the world? Is China and the United States, and then the rest of the countries. Okay, so this is the energy consumption in the world. So we have China, we have the United States, and the rest of the countries. Yeah, India and Russia, there are a lot of people here, but in terms of energy consumption, they are far from these two giants, China and the United States. China, they are burning a lot of coal. Yes, in the United States, they are burning a lot of oil and natural gas. Why? Probably because there is more coal in China, and there is more oil and natural gas in the United States. So this is countries make the most of their resources. What is the global goal? Well, we have to reduce the fuel consumption. But if we look at the global, are we concerned about Spain? Look at this. Spain is this tiny bar here. No, we are not. Are we concerned about Australia? No, we are not. Turkey, Italy? No, we are. Our concerns are China and the United States because they are consuming more than half the energy that is consumed in the world. Okay, so yeah, in all countries they have to enhance their renewable energies and all that stuff. Yeah, but if we want to solve the global issue, we have to address this. So we have to, yeah, China and the United States, they have to lead the rest of the world in terms of renewable energy, in terms of zero energy buildings, all that. Okay, so this is the energy consumption. And now the other parameter that is relevant is the cost of the energy. Okay, so here we are. This is the cost of the energy in the European Union. Okay, I have data from the European Union, from Europe, and the United States. That data is from 2018. Yeah, so probably there will be statistics about 2019, 2020 statistics. We will know, but I think 2018, it's something that we can trust. And within the European Union, we find that Denmark and Germany, they have the highest electricity. This is the price of electricity. So this is 100 kilowatt hours is around 30. We are talking about euros. Okay, so it will be like around $40. So that means that 1 kilowatt hour costs around 40 cents of dollars. 40, okay, 40. In Denmark and Germany. If we look at this, these are the blue one, it's excluding taxes, and the red one is with including taxes. So you see that half or more than half the price that they pay for energy is they are taxes. Okay, well, so this is what Europe is. Europe is a place, it's very nice, it's very, or it used to be, I don't know, before the pandemic, but we pay and we are paying a lot of taxes. I know that in the United States you also pay taxes, but not as much as in Europe. Well, this is what life is. And the price in Europe, the price of electricity in Europe, it's quite expensive. Okay. Why is it? Because in Europe there are not natural resources. There is no oil, there is no gas, and they have to bring all these natural resources, all these fuels from other countries, either from the Middle East, either from North Africa, either from Russia as well. But in Europe, there is no energy production. So well, we have to understand this. What happens in the United States? Okay, so in the United States, maybe you can complain about this, but there are a lot of places, most of them, that the kilowatt hour is less than 10 cents. Remember that in Denmark, it was around 40, this is 30 euros, around $40, 100 kilowatt hours. So 1 kilowatt hour is around 40 cents. So in most of the areas of the United States, the price is below 10 cents. Okay, so in Denmark or in Germany, the price of the electricity is 4 times as much as in the United States. Is it because of the taxes? It is, and it's because there are natural resources in the United States, and you don't, or in the United States, they don't have to bring gas or oil from other places. They can do it, but there are enough natural resources here. So that's a fact. When we look at this, when we look at the energy consumption in the United States, it makes sense that people are consuming a lot of energy in the United States because the price of the energy is very low. It is very low. So if it's not expensive, I can consume it. Does it mean that increasing the price of the energy, people will consume less energy? Yes, for sure. But is it good? No, it's not good. I mean, in terms of economy. But I mean, it's difficult, okay? Because if we increase the price of energy, we reduce the activity. That's for sure. If something increases the price, the consumption is reduced, and consuming energy is about producing things. It's about transportation. It's about buildings. It's about, so everything that is related to economics needs energy. to run. Okay, so if we increase the price of energy, we will reduce the activity, and the economics will suffer. So there's an answer to this. What about renewable energies? Yes, it might be an answer. So we can keep on the activity, or so we can going on with our activity, and we can consume the same amount of energy with renewable resources. So far, it's difficult. So we don't have enough, or the technology so far is not enough to continue our energy consumption at this price. So this is the debate right now. So what are we doing? We are going towards a renewable world. Yes, but we are in a transition. So transitions are always difficult because we don't know what's going to happen, and probably there are things that are not foreseen that will affect the energy consumption, the global economics. Anyway, I think this graphic is interesting because in New Hampshire is where New Hampshire, this tiny area of New England, is where the electricity has the highest price in the United States. So here we are talking about 17 or 18 cents, and here we are talking about 7, 9, 8, 9 cents. Okay, so this the price here is twice as much as in this central area of the United States. Why? I don't know. I'm not an expert on the geography or natural resources in the United States, but and this is in 2019. Okay, so I think this is up to date. But anyway, the highest price in the United States, which is 20 cents, it's half the price than in Europe. Okay, so that's why in Europe we say that energy in the United States it's not expensive, and people might think differently here because, well, 9 cents per kilowatt hour, it's expensive. Well, not as much as 40. Okay. Anyway, as you can see, there is not an answer to this. So why is the price in Alaska 19 and in Texas 7? There might be reasons. Yeah, there might be, but we need to know that. But suddenly changing the way Texas is consuming and producing energy, we can't do that overnight. So it's a long path. So that's why we have this goal, 2050, that all buildings have to be zero energy buildings. Most of the energy has to be from renewable sources, because you can't change a system overnight. But we need to understand that we are moving towards that direction. Will it change? I don't know. I don't think so, but we don't know. Anyway, we have the energy production, we have the price of energy, and that explains a lot of things. So probably the price of energy explains why Germany is at the top of the renewable energy production. It might be an explanation because they have a very expensive energy and they are moving towards this renewable. It makes sense. In places in which the energy is very cheap, maybe they don't need to move towards renewable resources. And I think in this area of the United States is where they're more active towards these renewable resources, more than in Texas, as far as I know. Okay. So we have energy consumption, we have energy cost. That explains a lot of things. And if we just connect the energy consumption and the energy price, we can understand a lot of things going on in the world. And then, but we are architects. We are not here to solve the global. Well, we are not. We can try, but our goal is to produce energy efficient buildings. So and it's too much. Okay, so if we can achieve this goal, we will be happy. And this is the energy consumption of different appliances we have at home. Okay, so we have appliances with high consumption, and we have appliances with low consumption. High consumption, it's the cooker, this kettle, the microwaves, the air conditioner. Okay, so these three things has the or have the highest consumption. The cooker, but how long are we using a cooker? A few minutes a day, a few hours, a couple of hours maximum. We are talking about an electric cooker. We are not talking about gas. Kettles or microwaves, again, how long do we use this? With the air conditioning, it's different because if it's too hot outside, probably we use the air conditioner for 4, 5, 6, 8 hours. Okay, so this has a high energy consumption, and we use this for a long time. And this is the worst thing that can happen. Okay, if we have something that consumes a lot of energy, but we use it only a few minutes during the day, it doesn't matter. But if we have something that consumes a lot and we're using this for hours, then it matters. So that's why reducing the air conditioning or the heating and cooling loads, if we are working with electrical systems, it's something that we need to do in order to achieve the zero energy building goal. Then we have computers, refrigerators. A refrigerator consumes, well, here's in the middle, and a fridge is connected 24 hours a day. Okay, so the fridge and the, well, but the air conditioning is it's worse. Okay, so we have to reduce heating and cooling loads. And then we have all these. Nobody's using incandescent lamps nowadays. An incandescent lamp, we know what this is, and it was great. So 50 years ago, it was a great technology because uh, we had artificial light. Nowadays, we have low consumption lamps like these ones, and especially we have LED lamps. Okay, so the first thing, if you are going to retrofit a building, an existing building, and you find that the lighting is made of incandescent lamps, this is the first measure that you have to take. Okay, replace all these lamps by LEDs. And it's quite easy because we only have to unplug this. Oh, we have to substitute the light bulb, and it's easy. It's not very expensive, and it will save a lot of energy. Okay, so this is the first measure that we have to take when we are retrofitting buildings. Everybody has done it already. Okay, so don't be naive and think, okay, I'm going to save the world and I'm going to replace all the incandescent lamps. Most of countries, they have already done it. So, and now what do we have to do? Well, we have to get to know basic concepts of electricity. This is not because we are architects. This is because we are human beings, and knowing basics about electricity, it's like knowing basics about literature or philosophy. So there are things that we need to know. We need to know who Plato was 2,500 years ago and what he wrote. We don't have to read all his books, but at least we need to know who he was. And we need to know something about electricity, and we need to know the units, and we need to know the basic features of circuits. Okay, and this is what I'm going to explain today. So I'm not going to do anything new because everything is in that book. Everything that I'm going to speak about today, it's taken from this book, from the Mechanical and Electrical Systems in Architecture, Engineering, Construction. And here you have the chapter 17, which is about the electricity theory. And I have taken these points, 17.3, 17.6, 7, and 8, because those are definitions that we need to know. Okay, so you can go over this chapter and you can read these points, and it's there. I mean, it's I'm not going to say anything that it's not here in that book. So those are the units. We have volts, ohm, amperes, watt, and volt ampere, and kilowatt. Okay, so we have the main units are these ohms, amperes, and watts. We know what a watt is because watt is the unit of power. It's the electrical power. Okay, so we have power in mechanical systems, in heating and cooling systems, and we have power in electrical systems. In mechanical systems, we have the BTU. Here in electricity, we don't have BTUs. We have watts. Okay, so that's why eventually we need to turn watts into BTUs or BTUs into watts. We have related this before. You remember the COP or the EER, the energy efficiency ratio. So those are coefficients that relate thermal energy and electricity. Okay, so eventually we need to relate both units. Volt is the unit of electrical potential or tension. It's named after Alessandro Volta. This guy. Alessandro Giuseppe Antonio Anastasio Volta. Wow, I love this name. He was a physicist and chemist, Italian, from the 19th century. In the 19th century, a lot of things happened. Okay, so all the physics that we are using now come from the 19th century. So there were a lot of scientists that invented most of things that we are using today. Okay, so this guy, he discovered the something. It wasn't electricity, but was the electric force. Okay, so there are four forces that explain everything in the world. The gravitational force, it was discovered by Newton, and then this guy discovered the electric force, how two particles are attracted. Particles with different charges are attracted, and that explains a lot of things. Okay, so Mr. Alessandro Giuseppe Antonio Anastasio Volta. So we have to thank him for.
Do it again. Do it again.
No, no, I don't want to. I have exhausted my Italian, so I'm not going to do it again. Then we have Ohm, and this is named after. I think there's a guy by the name of Ohm, or is not. Ohm is there electrical resistance. Okay, so there's a Georg Ohm. Okay, so this guy, he was from Germany, Georg Simon Ohm. This Alessandro Volta was from Italy, but they were all, yeah, he died in 1854. Yeah, so at the beginning of the 19th century, I told you that the whole world changed. Okay, so this Mr. Ohm, or the Ohm, the unit is named after this guy, and this is about electric current, but this is the resistance. Okay, so when we have electricity and we have a resistance, then we can turn electricity into other kind of energy. It can be light, it can be heat, but we need a resistance. Okay, so this guy enunciated the Ohm's law. So there's a law that is named after this guy. Okay, and Ohm is the unit of resistance. Okay, then Ampere. Is there a Mr. Yep, André Marie Ampère, a French guy. Okay, again, at the beginning of the 19th century. Yeah, so everything is named after someone that lived at the beginning of the 19th century. Okay, so all these things are related. So the amperes, it's the unit of electric intensity. Okay, so the volt is the tension, ampere is the electric intensity, and ohm is the electric resistance. Okay, interesting. And everything is related by the Ohm's law. So the Ohm's law relates resistance, tension, and intensity. And then everything is related because we need power. We have watts. Okay, and watt again. There's a Mr. Watt, James Watt. In English. Okay. Another, and when did he leave? Well, he passed away in 1819 again. Okay, so everything happened at the end of the 18th century and at the beginning of the 19th century. And what about Newton? Sir Isaac Newton. Okay, so he's younger because he passed away at the beginning of the 18th century. Okay, so Newton, well, he was the most important scientist in history of science. So it's too much. Anyway, after that, I think he set the basics for the modern physics. Okay, so after everything went. Yeah, but I thought he was well younger. I mean, he lived between the 17th and the 18th century. Anyway, all these guys are well, and if we want to talk about radioactivity, so it's there are scientists living in the 19th century. We talk about I don't know, other fields, hydraulics, so acoustics. So everything. There were a lot of people from different branches of physics working on different aspects. But yeah, so the 19th century, it was an incredible century with a lot of new things going on. Anyway, we need to know what an electric generator is. Well, usually we have water, and if we release that water from a height, it goes down, and then it makes a turbine run, and that generates electricity. So our a turbine, it's rotating, and that generates electricity. This is the hydraulic energy. But there are other methods. We can burn fuel, coal, diesel, gas, whatever, and that generates steam, and then it generates electricity going through generators. Okay, so everything is about generating movement, and then that movement generates electricity. We can move water, we can move vapor, steam, but we need either a lot of mass, a lot of water falling from height, or we need to generate this movement by burning things. Okay, but well, this is it. So we have the electric generator. Then we have a transformer. A transformer is another device that transforms the tension. Okay, so if we want to transmit this electricity, because usually we have a generation plant outside, so it's not within the city. Usually it's not within the city. And then we have to transport this energy. How can we do that? So there are wires, there are high tension wires, and we have to increase. We need to use at high voltages. So there's a lot of tension between those wires because the higher the tension, the less the power that we lose in the cables. Okay, so that's why in the middle of the field from the electric plant to the city, we have this high tension cables or towers. High tension means that if we touch two poles, this electricity is going through us. Okay, if we touch this and this, two different cables at a high tension, and our body cannot bear this high tension. Sometimes you have experience in houses. If you touch two cables, you feel like, okay, this is electricity, but we can cope with this amount of electricity because the tension is very low. But when the tension is very high and we touch this, then we get burned, literally. Okay. So we are working from, or we are transmitting this energy through the country at high tension, but then the electricity that we use at home, it's either at 140 or 120, sorry, or 240 volts. Okay, volts. And this is low tension. Why 120 and 240? I don't know. In the United States, it's 120. In Europe, it's 240. That's another issue, because when you buy some devices in the United States and you want to use it in Europe, they don't work. Eventually, everything will work well in different countries. I hope so. Then we have to enter in our building. Well, to enter in our building, we have this. We need a board. Okay, so in this board, we take the electricity or a wire that comes from the municipality or from the electric company or from whatever, and then we have a board. We have a meter, and then we control the electricity that we are using in our house or in our building. Okay, so the main or the first element is a main fuse. Okay, the main fuse is an element, it's a tiny element in which we connect the electric supply from the city or the electric company and the electric supply to our house. If there is an excess of energy because there's something wrong, a main fuse, it's a circuit breaker. Okay, so it collapses and it protects the installation. This is a drawing. This is what I'm talking about. Okay, so the high tension, we're talking about 12,000 volts. Okay, so this is what, well, we are talking high tension. It's 60,000 volts. This is the tension that comes from the electric plant. And then we have these towers and these wires. When we are close to the city, we have the first transformer and it reduces the tension. So we have all these cables that we can see on the streets. The tension here is 12,000. It's a lot. Okay, so it can kill people if they are in contact with this tension. Okay, but at least it's not 6,000 volts. So we have reduced this. And finally, we have so every time we change the tension, we have a transformer. So first we have a transformer close to the city or close to the neighborhood. Okay, so we connect these high tension wires to the transformer, and then we distribute this through the streets. But when we have a building or we have a campus or whatever, then we have another transformer, and then we connect this to the house, and the house, the tension of our devices is 120. So this is not, I mean, people can bear 120 volts for a while. If you are exposed to 120 volts for 10 hours, you will end up dying, I suppose. But at least if we touch this accidentally, we just feel like, oh, but it's not harmful. Sometimes we have this transformer drum here. Sometimes in our buildings, if the building is big enough, we have a transformer substation in our building. So I'm sure that in King State College, in the campus, there's something like this. There's a building itself, which is this transformer substation. Okay, so it takes electricity at 12,000 volts, and then it transforms this, and then it feeds all the buildings that we have in campus. There are buildings in which there are more power or more people than in some small villages. Okay, so when imagine that we have a mall, most likely those malls, they will have their own transformer substation. And in campuses where we have a lot of buildings together, and those buildings belong to the same owner, this is the case of King State College, there are different buildings, but they are all using, or they are all paying the same electricity bill. So probably there will be a meter here before entering this substation, and then it will be distributed in different buildings. Okay, So this is something that we need to know. We have this, we have an electric plant somewhere, and on the outskirts of the city, we have this first power transformer or substation. So we change the tension here up to 12,000. Then these wires, now I think it's mandatory. If you are doing something new, it's mandatory, something new, I mean, a new urban development. So it's mandatory that those wires are underground. You prevent a lot of accidents by doing this. But it's very expensive because 50 years ago it wasn't mandatory, and the electric companies did this. Little by little, they are doing this. So when they are well, I don't know, but it's extremely expensive doing this. So that's why in King, I think you still can see those wires on the streets with those vertical elements. Okay, but little by little, they are placing all these elements underground, and I think it makes a lot of sense. Okay. What else? We need to understand the difference between single and single phase or a three-phase system. Well, we need tension. Okay, so we can transmit this electricity, but we need tension. So that's why we need two wires. We need the line and we need the neutral. Okay, so in a device, we have a wire that is the line. We have another wire which is the neutral, and by connecting this to our device, we put together two electric currents, and then we have electric power. Okay, so if we want to feed a device, we need at least two wires. So this is the single phase. When we are talking about the single phase, that means that we have one line. This is what a phase is, and then we have the neutral. When we are working about three-phase system or three phases, that means that we have three wires in a neutral. So we will end up having four wires. What's the difference? Well, three phases, if the electric power is too high, we need three phases. It's more reliable, it's more efficient, and it's less risky. For single family houses, with the appliances that we have in a single family house, single phase or a one phase system, it's enough. But in other buildings, we need three phases. And then, well, these are the usual voltage that we have. It can be either 120 or 240. It can be 220, 230, 240. It depends on the country, or it depends on the device itself. But this is the difference: 120 and 240, or 110 and 220, something like that. And this is how a single phase system works. Okay, so we have the phase, we have the neutral, and we have tension between them. It can be 230 in Europe, 230 to 40, or it can be 110, 120 in the United States. Okay, but and then we connect devices to this cable and to this cable, to the phase and to the neutral, and then we have electric current going. Yeah, so that means that the electric current is going this way, and then we have electric current in the other direction through the neutral. Okay, so we connect this, then we can go this way as well, and then we can connect things in parallel like this. Okay, so we can connect different devices we can connect one device or three different devices. It depends, but there is always a limit, and that limit depends on the tension, it depends on the thickness of the wire, and it depends on the intensity of the current. Okay, so we will make a short exercise to understand how many devices we can connect to this. This is the single phase in Europe with 230 or 240. This is a single phase in the United States. Okay, so we have line 1, line 2, and we have a neutral. Between line and neutral, we have 120. And between two lines, we have 240. Why do we have this? Because there are devices that run at this tension, at 240. So in Europe, they have, okay, if most of devices are running at 240, so let's have this tension. In the United States, they have this system. So there are some devices running at 120. So you have to connect a line in a neutral. And there are other devices running at 240. And then you have to connect two lines. I think this is more complicated. Probably it's safer because the lower the tension, the safer the system. But anyway, if we have heaters, air conditioners, all these devices run at this tension, 240. Okay, so if we have, then we have to go to this first chart here. So with low consumption devices, we can run with 120. With high consumption devices, we need to 240. Okay. And what's next? Oh, this is important, the power factor. Well, the power factor, we have to assume that we can lose some energy with this system. Okay, so this is the electricity. It's like it has wave parameters. So if these two waves are not well synchronized, we can end up losing energy. So this is the concept of the power factor. So the power factor is the amount of power that we are losing. Okay, if the power factor is 1, that means that and we are not losing any energy. If the power factor is below 0.7, it's not acceptable because we are using like more than 30% of the electric energy in our circuits. And this is not acceptable because those are leaks. It's not safe. It's not efficient. Okay, so an acceptable power factor, it's something between 0.7 and 0.95. This is not for architects. This is for electric engineers. So they have to, when they are done with the circuits, they have to check the power factors are within those within this range.
You're suddenly 10 times later. I mean, that's true. That's basically 10
Our
times.
friend Tyler is not muted. Okay, but the power factor matters, and sometimes it explains electric consumption that it's not foreseen. Okay, so why am I paying that electric bill if the power of my devices is not as much? Well, because you have an issue with the power factor, and there are leaks or there are problems with your electric with the wires and the circuits, and you are consuming more energy than you are, or you are paying for more energy than you are actually consuming. Okay, so everything that it's 0.8, and this is what we use by default. We use a power factor of 0.8. We assume that there might be something that it's not perfect, but 0.8 is within the range, the range that it's acceptable. Well, three phases and single phases. When we have electric engines or electric motors, we have three-phase operation. So for example, in buildings, when we have an elevator, we have a three-phase system. When the heating system or the cooling system, it has a lot of power, we need a three-phase. Okay, so for electric, for lighting, for heaters, refrigerators, we can get by with one phase. But if there's something serious, if there's something like an engine or a motor, elevators, high power cooling and heating systems, then we need the three-phase because it's safer and we have more tension, because between three phases, we can have 420 instead of 240. Okay, when 240 is not enough, then we need a three-phase system. It depends on we say that in single family houses, one phase is enough. It depends on a single family house. If you have a single family house with elevators and 50 bedrooms, Probably you will need a three-phase, but if you have a single family house with a couple of bedrooms and 2,000 square feet, one phase would be more than enough. Well, this is too much. Well, the three-phase system, it's something like this. We have three wires, R, S, and T, or line 1, line 2, and line 3. And then we have a neutral. And then we can, if we have an engine or have the electric elevator, then we need to connect three wires to this. If we have other devices, we can connect the neutral to line 1, or the neutral to line 2, or the neutral to line 3. And if we have a three-phase system, we have to make sure that all circuits are balanced. Okay, so we have to connect the same amount, not the same amount of devices, but the same power to line 1, line 2, and line 3. Again, this is not something that we have to worry about. But at least if we are talking to the electrical engineer, because we know the power that our systems are consuming, we have designed the mechanical system. So we know that, okay, so I need these therms or BTUs, and I'm using this with this energy efficiency ratio or COP. So somehow we know the amount of energy that we are consuming. So if we are dealing with electrical engineering, I think there's above 15,000 watts. We need a three-phase. Below 15,000 watts, we can get by with only one phase. So at least if we know these rough numbers, at least we can deal with electrical engineers and we can find out whether they know what they are doing or not. We better find an electric engineer that knows what he is doing, because otherwise we're in trouble. Another important system, the earthing system. What is this? It is to protect a structure from lightning strike. Okay, so lightning, it's an incredible amount of energy, of electricity, that it's striking on our building. So we need to protect our building. So that's why we have this. So first, we have this element, and we connect this element. Eventually, we have to release this excess of energy into the ground. Okay, so eventually everything is connected into the ground, and there are wires and all this excess of electricity. We have to prevent this from damaging our devices. So we connect everything to the ground, and then we release this excess of energy into the ground. Okay, so the earthing system, it's important. It's a protection system, so it doesn't do anything but protect our building from lightnings when in the unlikely event that a lightning it's striking on our building. Maybe it happens only once in a lifetime, but if it happens, we need to protect our building with this. Okay, so we can have in summarizing this, we have a three-phase element. You see that in the American system, between the phase and the neutral, we always have 120. Between two phases, we have 200 to 10 to 20 to 40 between two different phases. And then we can end up having up to 400 between we can have 420 between other two phases. We have the earthing system, or we can have the simple one single phase. This is in Europe, and you have three wires because the tension is 110 or 120 between the line and the neutral. But a single phase needs the earthing system as well. So it doesn't mean that only three-phase systems need the earthing. So no, everything needs the earthing system. Okay, and this is what we have within our house. Okay, so we have a distribution board. So it's a board. It's not something huge. And we have different circuit breakers or fuses, and these are protection. Okay, so the circuit breakers are elements that when we have an excess of energy in one of these circuits, it pop, okay? So and it turns off this circuit. Why can it happen? If we are connecting, because everything depends on the thickness of the wire. Okay, so if we are connecting a lot of devices in this circuit and it's too much for the thickness of our wire, then the circuit breaker breaks the electricity as a means of protection. Okay, then we have distribution circuits. I want to go to transformers. Okay, this is what so this is a circuit breaker, miniature MCB stands for miniature circuit breaker. So we are all used to, and I'm sure that if you enter your house or your building, at the entrance, there will be a small box. You open that box and you find these kind of things. Okay, so these are the circuits that, so we have the line and the neutral. Okay, so when we, if it's connected, the line and the neutral, they are transferring electrons from one to another. If we break that circuit, that means that there is no connection between the line and the neutral, and then that circuit is stopped. Then we have this one, the residual current device or the differential circuit breaker. Well, here we are connecting the line and the neutral, but this is a protection device not for an excess of electricity. Okay, when we are connecting a lot of devices to this circuit, then this circuit breaker operates and stops the current, the electric current. That happens, or this happens, or this works when there is a leak. Okay, so that detects that there is a leak between the line and the neutral. When it detects that the intensity through the line and the intensity through the neutral is not the same, it means that there should be a leak. We are losing electricity at some point. We don't know where, but it can be dangerous. Okay, so it might be that one of the wires is not connected to anything, and if you end up touching this wire, you can get into trouble. Okay, so when it detects that at some point the neutral and the line are not connected or are not well connected, then we have this second safety measure. Okay, so we have the circuit breaker, and then we have this differential circuit breaker or residual current. Residual current is, yeah, so there are leaks and we don't know where, but something's not going, something's going wrong in the circuit, but it's not an excess of electricity. It's that the intensity that we have through the line and through the neutral, it's not the same. And finally, we have the main switch. Okay, so in the main switch, we have this one with two elements here. This is for the line and the neutral. And if we have four, this is a three-phase. We have three phases in the neutral. Okay, so depending on what kind of building we have or what kind of devices we are running, we have either this or that. Okay, so this is if we want to make sure that everything is stopped. So let's close this one, and all circuits are stopped. Okay, if we want just to, if we are replacing a light bulb or whatever, and we know the circuit, we just by dealing with one of these circuit breakers, it's enough. But if you are not sure, you'd better turn everything off. And now that means that as of this point, you don't have any electricity in your house. Okay, and this is the board. Okay, so in this board, at least you should be able to identify these three elements: the main switch, single phase or three phase, the circuit breaker, and this differential circuit breaker. This is basic, okay? So a human being should know this. If you open one of these boards, okay, so this is a circuit breaker, this is the main switch, and this is a differential circuit breaker. This is the thing we should Yeah, everybody should know this. And then connections, it's pretty simple. I mean, this is not electricity works, and it's a question of having more or less wire. But it's a piece of cake. I mean, so this is the main switch, this one. As you can see, the neutral and the line, this is a single phase one. It's connected to this main switch. If it's a single family house with only a few circuits, we don't even need the differential circuit. We need a differential circuit when, well, when it's more complicated, but this is the basic. Okay, so we can have different circuits, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 circuits, neutral, line, and they are both connected to the main switch. Okay, so this is we have the supply. Look at this, the supply, it's always 3 phase. So you see that in this vertical element, we have 4 wires. We have 3 phases in the neutral. If it's only a single family house, we can just connect one of the phases, one of the lines to our house. So the line, one neutral would be enough. In a urban perspective, someone in the municipality has to make sure that the number of buildings or houses connected to 3 different lines are the same. But again, this is not something that we can check. So that comes from the electric, especially the electric company, not even the municipality. So they have to make sure, and they can check this in these transformer stations, that all lines are having the same load or are giving the same power. Okay, so that's it. Here, yeah, so here, this is a little bit more complicated because we have the main switch here with the line in the neutral. These are circuit breakers, MCBs, and this is the residual, what do you call it, current device. Yeah, so this one. Okay, this is more, well, this is more complicated. We have circuits, then we have the differential circuit breaker here, and the main switch, and we have the earthing. Okay, so at least we have 3 different colors. We have a color for the line, we have another color for the neutral, and then we have a different color for the earthing system. So this is what this main board is in single family houses. And those are colors. If we have a single phase, usually it's brown. The neutral, usually it's blue. And if we have a 3 phase, we have the brown, the black, and the gray, and the blue one. And the earthing, it's always something, usually we have this green and yellow. So it's very easy to understand what the earthing is, or it's kind of white. Okay. But well, this is the color code for this. So if we are looking at this, yeah, we should be able to understand what the neutral is, what the phase is, and what the earthing is by looking at the color codes. Okay, this is a one wire diagram. Okay, so this is something that we will see. We are not producing this kind of, but this is a document. When we are designing buildings, we need this kind of documents. Okay, so if you look at this, it's quite easy to understand. So first here, we have to understand that this is just one wire. If we have 2, you see that we have 2 dashes here, 1, 2. This is single phase. If we have 4, 1, 2, 3, 4, this is a 3 phase. Well, this is a complicated building because we have elevators, we have a pumping system, we have a heater. Okay, so this building, it's a public building. This is not a single family house, and it's more complicated because we have divided this in different in different circuits. When we have an elevator, we always have a circuit for the elevator. The elevator is it's an electric consumer. So every time we use an elevator, we are consuming a lot of electricity. Okay, so if you can go upstairs, it's better for health and for the global environment. Then pumping systems, well, it's something, it makes sense. So we need to divide these circuits. First, if we have something that it has a lot of power, we need a circuit only for these elements. So elevator, then pumping systems. There is no, it doesn't make any sense having the same circuit for the pumps, for the water pumps, and for the lights. It doesn't make any, or for the power sockets. Okay, so usually we have lights in one circuit, we have power sockets in another circuit. If we have a heater or this is the air conditioning or heating system, we have a different circuit for that. For the pumps, if we have a lot of pumps in a building, especially a high-rise building, in which we need a lot of power because we need to pump the water up to the fourth or the 40th floor or whatever, or we need elevators. So we have to divide circuits with common sense. Okay. All lights will be connected to the same circuit. All the power sockets will be connected to the same circuit. If we have something that with a lot of energy consumption, so let's have a circuit for this. Here you can see the numbers. Okay, so this is the power. The elevator uses 7,500 watts. The heater, 5,000 watts. The pumping system, 5,000 watts. The power sockets, only 600. The lights, yeah, here we have light ground floor and light staircase. Is it good having two circuits? The more, the merrier, I would say. Look at this. This has only 320. So we can easily connect this and this, and we will end up having 1,000 watts. That's fine. Why do we have to divide this? It's because of the use. Imagine that we have a ground floor, and then we have a staircase. Yeah, so there are two different things. So the staircase, probably it's a public area. The ground floor, maybe it's a private area. So having two different circuits, if there's an issue in the staircase, I don't have to cancel all the lights of the ground floor. Okay. So again, it's not something that we want to care about, but at least talking to the electrical engineer, at least we should understand what he is doing or what they are doing, this electrical engineering company. And we have to agree on that because eventually it's our responsibility. It's our building, it's our responsibility. We have different circuits. So here we have breakers. If the building is complicated, we need these differential breakers or this residual current breaker. Okay. And finally, we have the main switch here. But if you look at this, you should understand, okay, the power that is connected to each circuit. That's something that we need to check. Okay, yeah, so if it's above 5,000 watts or 5 kilowatts, yeah, I think it's better having a circuit for that. If it's more than 15,000, we should have a three-phase. In this elevator, if it's just a floor, maybe we don't need a huge elevator, and that's working well, only one phase circuit. But I would, yeah, I would rather have three phases here for this elevator. Anyway. And then we have to dimension the breakers. You see here that we have 10 amperes or 16, 32. Okay, so I'll show you how to dimension this. It's quite easy. And it depends on the power. Okay, but once you have done this twice or three times, okay, so the lighting system, we need a 10 ampere circuit breaker, and that's it. So it's easy. We have the circuit breaker, the differential circuit breaker, all these elements. Oh, this is the explanation of the power factor. Okay, so the power factor is the relationship between the true power, the power that we are using, and the apparent power, which is the power that we are consuming. Okay, so we have this. If the power factor is 1, the apparent power and the true power is the same. If the power factor goes down, so this angle, it's getting bigger and bigger, because the difference between the apparent power, the red line, and the green one, it's yeah, so we have this blue, and this is the power factor. Okay, so we have to reduce this blue line by making this. So if it's 1, we don't have any blue line. If it's growing, we are making that bigger. Okay, so power factor 0.8 is something feasible, and that's the explanation. We have two different phases, so we have to make these two phases, or these two wires, or these two waves. Okay, so if there's a difference between these two waves, this is the power factor, so we have to reduce it. That means that we are consuming a lot of energy, that we are wasting energy. So we are wasting all this energy, so we have to reduce that waste. Again, this is something that the electrical engineer company should do. They have to check that the power factor is within these limits. But at least we can ask for this certificate. Okay, so as architects, I think we have the commitment to okay, can you show me please the certificate of the power factor? And if they have tested the installation of the power factor is within the limits, we can sleep safe and sound. And okay, just 2 examples here. Probably this Thursday we will have a test because you have to work with a formula, just this formula. And so we will have a test with simple exercises like this, and then you have to type the correct answer. But it's I'm going to show you these 2 examples because it's a piece of cake. So this is a fluorescent lighting fixture, has a ballast. Do you know what the ballast is? Okay, so when we have a fluorescent lamp like this, well, I told you that nobody's using incandescent lamps nowadays, or light bulbs. Fluorescent is not a new technology. It's been here for, I know, when I was a kid, I remember that we changed our light bulbs at home by fluorescent, but these fluorescent tubes. So it should be like more than 30 years ago, 40, I don't know, a lot of time ago. So this is another new technology, but well, the ballast is the element that regulates this, and eventually the electric wires are connected to this ballast. Okay, so this work, yeah. So this is associated to this fluorescent lighting. Anyway, the power is 185 watts. We have to determine the number of fixtures of these ballasts that we can connect to a 2-wire circuit protected by a 20 amperes circuit breaker if the power factor is 0.8. Okay, it sounds like Chinese maybe, but now we have to understand what it means. This is the power of each fixture of each lamp, and then we have to determine the number of lamps that we can connect. We have a 2-wire circuit. A 2-wire circuit is a single phase because we have the line in the neutral, and it's protected by a 20 amperes circuit breaker. Okay, so if we look at this is the power. Okay, So the question is how many, we have 185 times how many fixtures we can connect to this circuit. If this circuit breaker is 20 amperes, look at this, this is 10, this is 10, this is 16, this is 10, okay? So this is the, yeah, the intensity that can run through the circuit breaker before it breaks the circuit. So let's do it. Well, let's keep this one and let's work with, because I'm doing this for Europe and for the United States, let's make it simple. So we have a 120 volt circuit. Okay, so this is our tension. So it's an American system. So we have 120. And the power equals the tension times the intensity times the power factor. Okay, so this is the formula. That's the only formula that you have to memorize. Power equals tension times intensity times power factor. Okay, so what is the power? What is the tension? 120. What is the intensity? 20 amperes. And times the power factor, 0.8. Okay, so we multiply the tension times the intensity that can run through the circuit breaker, 20 amperes maximum, times this power factor. So we have 1,920 volts amperes. Okay, so well, yeah, VA, this is the unit. And then if our device has a power of 185 watts, then we have to divide this by 185, and we have it's 10.37 units. We cannot have 10.37, so we need well, fixtures, lamps. So that means that we need 10 lamps. It cannot be more than 10.37, so it has to be less because we don't have a 0.37 lamp. So, okay, so that's it. So that's the only formula we have to memorize. Power equals tension times intensity times power factor. There's a different way to ask for this. So if we have 16 100 watt incandescent luminaries, okay, so this is out of date because they are using incandescent luminaries, okay, or lamps. Say this is a lamp. And the circuit will be operated approximately 10 hours per workday. Well, if we are not operating this continuously, the power factor is different. Okay, but when we are working with this continuously, more than 3-4 hours a day, we have this kind of power factor. Okay, so this is. Then we have to determine the circuit rating. So what we have to determine here is the circuit breaker. Okay, so what we have to determine is what kind of circuit breaker we need. And we are working with a 110 volts two-wire lighting system. So this is one phase. So we have this formula: power equals tension times intensity times power factor. But now what we are determining here is the intensity of the circuit breaker. So we need to calculate the intensity. So intensity is power divided by tension times power factor. What is the power? If we have 16 fixtures, 100 watts each, so this is the total power, 16 times 100. And then we have to divide this by the tension times the power factor. So how much is this? It's 1600 divided by 120.8. So this is 16.66 amperes. What are the sizes of circuit breakers? Okay, commercial circuit breakers are 10 amperes. 10 amperes. I think 20. 35. 40. Okay, so if the intensity is at least 16.6, we need a 20 ampere circuit breaker. So this is what we have. You see that there are 16. Oh, so they are also 16 amperes. Okay, but if it's more than 16, we have to use the 21. And there are 25. Okay, so those are commercial elements. So we have 16, 25, 20, 16. So here we have different circuits. So probably if we have a circuit with 16 lamps, 1,100 watts each, we need here a 20. So this has to be a 20 ampere circuit breaker, and that would be the final result. Okay, so this is the only thing that we need to know in this course. If you want to study electrical engineering, for sure there will be other things that you have to know, but we have this formula, and this relates the power, the tension, and the intensity. We have always this power factor. If we are in a perfect building, that power factor will be 1. But 0.8, it's good enough. And then sometimes they are asking us to calculate the power or the tension or the intensity. Okay, so in this first exercise, we have to calculate the power, and then we have to calculate how many fixtures. We have this power per one fixture, so how many fixtures we can connect to this circuit. In this second case, we have the total power, and we need to calculate the intensity of the circuit breaker. So we have to calculate the intensity that runs through this element, through this circuit, and then the circuit breaker has to be the one that it's above this value. So if it's less than 10, we can use a 10. If it's between 10 and 16, we use the 16. If it's between 16 and 20, we use the 20, and so forth. Okay, on Thursday, I'll make a couple of exercises again, and then you will have a test on this, but we are going to use always the same formula. Okay, so we are calculating either the tension, it's always something that we know. If we are in the United States, it's 120. If we are in Europe, it's 240. Okay, so the tension, it's something that we always know. So we either have to calculate the intensity or the power, but we are always using this the same formula here.